Hello. So I'm going to talk about the equations and the graphs that we were given, or graphs that I found, and sort of describe the motion of the helicopter, sort of like a diagram, that's on Mars, obviously. And so what I found was up here, I took the equations of position, velocity, and acceleration into their x and y components because they're vectors. And so what we have here is if we think that way is positive x and that way is negative or positive y, we have a linear, we have a linear acceleration, but negative constant going down. And then we have a quadratic, well, half of quadratic on the positive side, of velocity going down as well, because concave down since acceleration is negative, and a position that is cubic, but only on the x side, only on the positive side is kind of looks like a quadratic, but imagine there's also a negative here. And kind of what it makes sense because, they're the integrals of each other. It increases in power as it gets bigger and bigger. It makes sense. Or rather, as it gets smaller and smaller. From acceleration to velocity, it increases in power, and from velocity to position. And what that position shows, if we're looking at the motion of the helicopter, what that position really shows is the helicopter kind of just moving. Like if we thought of just the X of the helicopter, sort of like the shadow of the helicopter on the ground, it would just be moving forward and backward because it does return back to the origin. So it would just be actually just moving forward and backward. And obviously, if it just moved forward and backward, it would end up back at zero. And it doesn't really make sense. But that's where the Y component comes in. And this is sort of what the Y looks like if the angles alpha and beta were positive. I just graphed them out as positive. And big T here is the halftime of the flight. Approximately this middle point and also here as well. And then, so again, we have acceleration, velocity in the middle and position. And it makes sense again for powers wise. And sort of, sorry, actually this should be position this one and velocity this one, or acceleration and position. And it also makes sense because height wise, this is y, so height wise it's increasing in power again. And what this height shows is the helicopter, if we think about it on the vertical axis, goes up and down. And since they're both vectors, we're going to add them together in order to find the actual position graph, which we were also given that. And if we again think of this as positive and this as positive, because of the camera, it's the other way around. Adding the two vectors kind of makes something like this, adding the position one over there for the X and the position one for the Y over back here. And so the helicopter, as I said, would be going back and forth on the X, but since we have a Y, it kind of just, the Y coming back down to zero is where the helicopter stops. So that's about it.
Okay. Hello, my name is Jacob Herkenrath, and I'm going to be presenting the explanation side of things. So, okay, sorry, this is all acting weird. Okay, so the first thing we're given is the acceleration equation, and the first thing we're trying to do is find out what each variable means. Right off the bat, we see that beta and alpha are both angles primarily, and this would make sense given that the angle would change how far in which direction it went. And well, beta for this example would be changing the angle in the x direction, like unit circle on the x-axis, and then y would be a unit circle on like the y-axis, and that basically angles around. And then the other unknown variable is capital T, which we are actually given in this is an unknown constant. And we're gonna have to solve for that later. And then we also have t, lowercase t for time. And those are the equations. The x hat and y hat is very important to note here. That means it is a vector, and we'll be using that later. So we're gonna find the velocity first, given acceleration, which is the antiderivative of acceleration. We are given acceleration, we're gonna find the antiderivative. See here, I did it, we're doing it with respect to time. You do it with respect to time and not the others because time is a thing that we can calculate over a distance, and we generally want to know what it is in regards to time. And we get this nice equation where negative beta t squared over 2t plus, you know, that whole thing. Then we find the zeros of vt to see where it takes off and lands. And it is important to note here that we find the zeros because, first of all, for y, we want to make it 0 right off the bat because we want it to be on level ground, which is going to be at 0. And then we want to see where the next time it is at 0. We already are given one of our initial where it's taking off, where we know that it's 0 at, which is t equals negative t, negative big T. And so we can accurately plug that in and say Vt equals negative t. And then we also can plug in negative t into this and get all this stuff. And if you were able to, again, the 0 is 0. We made y 0. And then we also did some algebra, take the 2 over, and then we can isolate velocity initial x direction by itself, and we get bt over 2. And this is useful for another thing. Also to note here that also we get capital T as being our final one where it's going to land over. So now that we find that velocity initial value for the x axis, we can plug that in to our velocity so we can get a neat kind of integral here where we can take it with respect to time again. And notice that our velocity initial y is 0 again because it was 0 at the bottom. And then we integrate and we get the equation for position. So we're gonna then plug in the initial and final position to find the distance. And there's a lot here. Basically, our initial position is negative t, and the final position t we got by zeroing it out. So we're going to plug both of those in, one for the x of the vector to find it in the x direction. So negative t and t. And we see plugging it in right here for both negative t and t. And we're going to get negative beta t squared over 3 plus beta t. And that simplifies out to 2 beta t squared over 3 equals the distance. And it is important to say that we are taking final minus initial for delta x, basically the change in position, and change in position is that distance. So that's why we are equaling it to d. And then we're going to do the same for y, where we're going to plug in both the zeros, negative t and big T. And we are going to get this kind of rounded out 2 beta t squared 1 over 30 minus 1 over 42. Again, calculations, and then we get a simplified 2 alpha t squared over 105. And from there, we now solve for t using the delta x and delta y equations, where we plug in and find distance, where it's 2 beta t squared over 3 equals d. Excuse me. And then since we have that, we're going to try to isolate t squared by itself, which we can do by just doing a couple of math algebra stuff. We get t squared equals 3d over 2 beta, which looks awfully close to our delta y equation. So we plug that t squared into here, and you could see that it kind of cancels out nicely to get alpha distance over 35 beta, which means that all we need now to find the actual distance is the angle at the certain point, which would be alpha and then beta. And since beta is the x angle, and alpha the a angle, the y angle, sorry. So that's all we need to solve it.
Hello, my name is Jules Beyer, and I will be going over the reflection portion of this project. And so I would like to first start out by talking about how we used, or how we learned about how to use integrals in physics. For example, in this Get Ready activity, this video describes how to use integrals to find acceleration and velocity and position as functions of time, as well as finding final positions in X and Y planes. So we learned here that acceleration is a derivative of velocity, and so we can then use an integral or the antiderivative to find velocity from the acceleration position given in our project. And then we also learned here how to use integrals to find final positions. Another really helpful problem that we used in class was this Mario problem, in which it really helped us learn how to break down equations and look at what each symbol represents and how to make sense of things by plugging in units and just breaking down what each part means and how to make sense of them. So then we can apply that to more complicated problems like the one given in this project. This problem was a little bit different in that they wanted us to find Mario's initial velocity and when Mario's velocity returns to his initial velocity, whereas in this project, we were just looking for the final position as well as how long the helicopter was in the air. So I think overall, these problems in class, as well as our Get Ready activities, really helped us, really prepped us for more complicated problems like this one. And overall, they were quite similar. And I think especially in helping us break down each symbol in the problem to help us better figure out where we need to go from there. Thank you. Was that anything? Let's see.